So I'm going to walk through example problem 4.2 from your textbook. Here we have a simple deck, but you'll notice that this simple deck is not symmetrical. So we have columns that are spaced at 6 feet in this direction, 8 feet, and then 16 feet and 12 feet. So we can see the effect that this will have when we solve the problem. There's two parts to this problem. The textbook only really asks about the second part, the load on each column support, but as an intermediate step we're going to find the loads on each beam as well. The load on each column support is, again, would be what happens at the bottom. So if we have a footing at the bottom of this column or this column, the question is how much load is coming down on that footing. When we talk about the load on each beam, here's one beam along column line A. Here's a second one on B, and a third one on C. So before we start, I want to make a few observations. First of all, if we look at the beams, because this edge beam here along column line A is along an edge, as is C, we would expect them to take less load than the beam along line B. And since the spacing between A and B is 6 feet, and the spacing between C and B is 8, make a few observations. First of all, I would observe that the beam along column line A, because the distance between A and B is only 6 feet, would have the least load on it. The beam along column line B, because it's in the middle, is going to have the most load, and C would be in the middle, would have the middle amount of load. Also, if we look at the columns, we'll notice that the column at A3, so I'm looking at this one right here, because it has the smallest dimensions, 12 and 6, to the next columns, I would expect this foundation to be the least loaded. And because there's a column right here at B2, I would expect that to have the most load. Using the terminology in the textbook, we have what's called tributary area. And so looking at these four observations here, the tributary area for the beam on line A would be, we'd split this right down the middle, and we'd get 3 feet here and 3 feet here. So each one of these is 3 feet. And the tributary to the beam on line A is this area here. So it's 3 feet by 28 feet. The tributary on column C would be similarly over here, 4 feet over, and it would be this area here. Okay. Now if we look at column line B, we'd make those same lines, 3 feet on this side, 4 feet on this side, and so the tributary to the beam on column B, line B, would be the 3 feet plus the 4 feet would be 7 feet. So the amount of load on each beam is going to be proportional to its tributary width. Similarly, if we look at the columns, if we split these up in half, we can see that the column at A3 has a tributary area here of 6 feet by 3 feet. So the tributary area is equal to 18 feet squared. And if I look at the column at B2, we're going to have to split everything in half. And the tributary will be this area in here. So what I have is 8 feet here and 6 feet there, which gives us 14 feet, and 3 feet and 4 feet, which gives us 7 feet. So the tributary area for the column at B2 here is equal to 7 feet by 14 feet, which is equal to 98 feet. So if we add this into a table over here, we can see beam A has a tributary of 3 feet, beam B has a tributary of 7 feet, so width, tributary width. Column A3 has tributary of 18 feet squared, so that's a tributary area, and then 98 feet squared. So again, the load on each of these members is going to be proportional to their tributary. So let's go through and work through these one by one. The first thing we need to look at here is the loads. When we look at these dead loads and live loads, you can see we have a deck load of 8 psf and a live load of 60 psf. With the units of pounds per square foot, those are surface loads. So the dead load is basically the weight of the planks themselves, and we can kind of visualize this as if we took a 1 foot square on the deck, the load on that 1 foot square would look like this. Okay, so we have that much load on there. So what we do is when we're looking at areas on the deck, we have to apply what turns out to be a total of a surface load is equal to 60 psf live load plus 8 psf dead load. And that gives me a total of 68 psf on the deck. When I'm looking at a beam, and let's start with beam A, to find the load on beam A, so let's look at beam A. I'm going to draw it here. Beam A goes from column line 1, 16 feet over to column line 2, and then 12 feet over to column line 3. And what it's going to see is it's going to see a distributed load that looks like this. And that distributed load is going to be made up of two components. The load from the deck, this value right here, 68 pounds per square foot, and the beam self-weight of 10 pounds per foot. Okay. Notice that those have different units, pound per square foot and pounds per lineal foot. So what we need to do is we need to multiply to get this weight here, W. I need to multiply the surface load by the tributary width of 3 feet, and then we add that to the beam self-weight. So let's do that right down here. We have W is going to equal the surface load times tributary width, okay, plus the self-weight. And if we put these in here, what we get is we get 68 psf times 3 feet plus 10 plf. This gives us 204. The feet cancel with one of the square feet in pounds per square foot, plf plus 10 plf, and we get a total of 214 plf. So the weight on the beam itself is W is 214 plf. Okay? Now note that this, if you look real closely here, you can see there's a division in the two beams. So this is actually two totally separate beams. So all we've done here is found the uniform load on the beam due to the live load of 60 pounds per square foot, the deck load 8 pounds per square foot, and the self-weight of 10 pounds per square foot. Let's do it again. Let's do the beam on line B, and the only thing that's going to be different on this one is the tributary width is going to change. So let's look at the line B. So this one is on line A, and this one is on line B. Okay. Again, W equals the surface load times tributary width plus self-weight. So we have, again, 68 pounds per square foot times, this time our tributary is 3 feet on the left and 4 feet on the right, to a total of 7 feet. And then we have 10 PLF pounds per lineal foot of the self-weight of the beam. This gives us 476 PLF plus 10 PLF for a total of 486 PLF. Confirming what we estimated at the beginning, that column line B, the beam is going to be loaded heavier than column line A. So W is 488 PLF. Okay, so column line C, we'd work it out the same way, only we'd just use a tributary width of 4 feet. So let's go back up here. What other question are we asking? We're asking the loads on each column support. So what we can do is we can look at how much each beam is contributing to each of the columns, or we could use this method of tributary, which I think is a little bit more direct. And what you can do is you can actually do it both ways to check your answer. So let's take a look at the first one, which would be the column A3. And let's look again at the tributary of the column at A3. It's half of this bay plus half of this bay. So the tributary here is that. Okay. So we need to pick up all the weight that's included in that area. So let's look at column A3. Okay. We have a tributary area this time of 6 feet by 3 feet. 6 feet here, 3 feet there is 18 feet squared. So what we need to do is we need to multiply the surface loads times the tributary area, and we get 68 PSF times 18 feet squared, which gives us a total of 1224 pounds. You'll notice we're taking pounds per square foot times square foot, and we're left with units of pounds. Now, the question is, how do we deal with the beam? Well, the beam is just running 6 feet, but doesn't run in the 3-foot direction. And you'll notice the beam has units of pounds per lineal foot. So, we need to multiply, we need to get the weight of this chunk of beam right here. So if each individual foot weighs 10 pounds, that's what 10 pounds per lineal foot means, then we have 6 feet of beam, therefore we take the beam load times its length within the tributary area. So we don't take the full 12 feet, we just take half of it, which is 6 feet. So in this case we get 10 PLF times 6 feet, and that's equal to 60 pounds. Notice we can't add up our total force on the column till we have it in consistent units of pounds. So what we've just determined now is we have 1,224 plus 60, or 1,284 pounds being applied to the top of the column right there. So the top of the column, so if we look at the column now, we have 1,284 pounds being applied to the top. We have to add to that the weight of the column. So the column load is already in pounds, so we just add that in, 100 pounds. Now, if we were told the column was 10 pounds per lineal foot and 10 feet long, we would do the same thing as we did with the beam. So our total force applied at the bottom of the column, which would be the force we design a foundation for, would be the sum of these three numbers. 1224, 60, and 100 is 1384 pounds. Now let's look at column B2. Okay? And if you look at it, it's in the middle. Let's go back up here. And again, we're looking at the column at B2. So it's the column that's underneath this point here. And to get the amount of tributary to it, we're going to split the bays in half. Like this. And we end up with this area tributary to the column. Okay? And so we're going to have 8 feet there, 6 feet there, 4 feet there, and 3 feet there. 7 by 14, again we found that was 98 square feet. So we need 98 square feet of area. So we do the same thing as we did with column A3. We take 68 PSF times 98 feet squared, and we get 6,664 pounds. So how do we deal with the beam? Let's go back up here. The beam is running along here, along column B, line B, but we're only worried about the weight of the beam that's within our tributary. So if you can kind of picture the piece of beam below here, right here, we have 6 feet, 8 feet of the beam on this side, and 6 feet of the beam on this side. The beam still weighs 10 pounds per linear foot, so because the beam is running the 14-foot direction, we take 10 PLF times 14 feet, and we get 140 pounds. Okay? So now we've taken care of the deck. So this here is the deck and the live load. This is the beam, and then we have a column. Again, the column itself weighs 100 pounds. Which gives us 6,904 pounds. Okay? So to summarize, we end up with the beam on column line A has 214 pounds per linear foot uniformly distributed over the beam. So it's a linear load. The beam on line B, 488 pounds per linear foot uniformly distributed over the beam. The column at A3 at the base of the column, so including the weight of the column, 1,384 pounds, and 6,904 pounds at B2. The last step is always to check your work. So go back to the beginning and we'll look at what we observed. We expected the loads to be the greatest at A3, the greatest at B2 and the least at A3, which is what we found. It's always good to check your math. 204 plus 10 is 214. We have 1224 and 60 and 100. That checks out. 476 and 10. Looks like we made a little math error here. This is 486 PLF. Okay, always good to check your math. And 6664 plus 140 plus 100. And it checks out to 6,904. So what are the take-home messages here? The take-home messages are being able to visualize that what areas or lengths are contributing to each structural member, understanding that when we have loads that are in units of surface loads, pounds per square foot, we have to multiply those by areas. When we have loads that are in pounds per linear foot, we have to multiply those by lengths. And when we have units of pounds, we don't multiply those by anything. Now, it would be good for you to go ahead and do the same thing I did. Try to find the load on the beam in column line C, and one or two of the other columns, say A1 and B1.